Hello, everybody. We will start the webinar now. My name is Nissim Asida, and I am the Ophir Optics Director of R&D and Engineering. I welcome you to our Fiber Laser Optics webinar. As an introduction, Ophir Optics is a manufacturer and designer of high-power laser optics for 1-micron fiber lasers and CO2 lasers. And in this webinar, I will focus on the optics for 1-micron fiber lasers. As a session guidelines, I welcome questions and comments. Please write them during the session on chat, and I will answer at the end of the presentation. And you can also send me email. You have my email address in the presentation. In the slide that you are looking at now, you can see my email address. So please send me emails if you have any questions or comments. So this webinar has 3 sections. First one is standard optics. I will describe the standard optics used in cutting heads. The second topic is annular beams. I will explain what we mean by annular beams, what is it good for, and how to achieve it. And the last topic would be zoom optics. So let's start with standard optics. On the left side of this slide, you see a picture of a cutting head. On the right side, you see the internal optics of the cutting head. We start with the laser, which has a diameter of D0. The fiber core has a diameter of D0. The beam, which is exiting from the fiber, is diverging, and therefore you need a collimator lens here. The collimator lens has a focal length of FC, and it collimates the laser beam. Then you have a focusing lens, and the focusing lens is focusing the beam to a small spot size where you cut the metal. The diameter of the laser spot size is denoted by DF and is calculated by the ratio of the focusing lens focal length to the collimator lens focal length multiplied by the fiber core diameter. So, as you know, if you want to cut different materials with different thicknesses, you need different spot sizes. So in order to change the spot size of the laser beam, you should change one of the following parameters: either the laser core diameter, the fiber core diameter, or the collimator lens, or the focusing lens. You must change one of these parameters in order to change the spot size to fit your cutting conditions. In this slide, you see the structure of a collimator and focusing lens. So in the standard case, if you use conventional optics, spherical lenses, you need 2 lenses in order to collimate the laser beam or focus the laser beam and still get good performance. However, if you use aspheric surface, you can remove one optical element and use only one lens and still maintain good beam quality required for cutting. This is achieved by the aspheric surface. The advantage of using aspheric surface is that firstly you use only one lens, and consequently the absorption is decreased by half. Now, the absorption is one of the most important parameters in laser optics. Because of the high powers of the laser, even a small amount of energy which is absorbed by the optics can cause damage or a degraded quality of cutting. Therefore, you want to have absorption as small as possible. Minimum absorption is required. And if you use aspheric lens, the absorption is reduced by half. So this is a very important factor and advantage of using aspheric lenses. This slide lists the parameters which has to be taken into account when designing the coating of the optics. One of the most important features of any optics, and especially laser optics, is its coatings. So in order to design the right coating, we must specify and take into account all these parameters. So the first parameter is the laser wavelengths. The range of wavelengths in fiber lasers is between 1030 to 1070 nanometers. Sometimes we want to focus on a single wavelength, let's say 1064. But in other cases, we would like to cover the whole range between 1030 and 1070. So the first parameter to specify is the range of wavelengths. The second parameter is transmission or reflection. Usually, you want maximum transmission and minimum reflection. If you have reflection in the system, you get laser scattering. And the scattering of the laser beam can cause damage and also heat up the mechanics and the optics. And this could distort the laser beam and degrade the cutting quality. Therefore, you have to specify what is the transmission required and what is the reflection required in each case. The next parameter is angle of incidence. Typically, our optics cover angle of incidence of 0 to 15 degrees. Any value in this range should be fine. Then we have to specify the optics mechanical characteristics. Another parameter is transmission in the visible, because sometimes you have, in addition to the laser beam, you have a visible beam which assists us when cutting the mechanics, when cutting the substrate. Another very important parameter is LIDT, which is laser-induced damage threshold. Each optics has its own LIDT value, and when we design the coating, we must know what is the expected laser power and beam diameter in order to make sure that the optics will not be damaged by the beam. So we must make sure that the LIDT of the optics is much higher than the intensity of the laser beam. Next parameter is the raw material, of course. The typical material for 1-micron optics is fused silica, but there are many grades, and we must specify the precise grade that we are going to use. Another parameter is the coating materials which we use. We have a variety of coating materials. Each material has its own advantages and disadvantages, and we must take it into account when we design the coating layers. Next parameter is the deposition process. The coating has many processes and many options for deposition processes, and we must choose the most appropriate process for our design, for our coating design. And lastly, we must take into account the environmental conditions of the optics. The above data will enable us to control the following characteristics of the final optical element. Absorption, as I said, absorption is a top priority in terms of performance. Absorption should be as low as possible. Secondly, reflectance. Reflection also should be minimal, but typically there is a trade-off between absorption and deflection. If you want to achieve the minimum absorption, you will have to compromise on reflection, and vice versa. If you want minimum reflection, you will have to compromise on absorption. Transmission is the opposite of reflection. If the reflection is minimum, transmission is maximum. LIDT is the laser-induced damage threshold, and we have to make sure that the LIDT value is high, and in this case, if it is high enough, the optics will not be damaged. And the last parameter is mechanical characteristics of the coating and the optic. On this slide, we see the specification of one of our coatings. It is an AR, which means anti-reflection coating. V-coat means that the coating has a specific wavelength in which its performance is optimal. In this case, it is optimized for 1064 nanometers. And this specific coating also transmits in the spectral range of 650 to 670 nanometers. And this is for the visible red light. The angle of incidence range of this coating is between 0 to 15 degrees. The reflection is 0.2% at the range 1030 to 1070 nanometers. Transmission in the range 650 to 670 nanometers is above 60%. Now the transmission depends on the wavelengths. The best transmission, as I said, is at 1064, and it is above 99.8%. If you are at 1030 or 1070 to 1080, then transmission drops to 99.6%. Still very good, but not as high as at 1064 nanometers. The absorption of this coating is below 50 ppm. ppm is part per million. So this amount of absorption is very, very small, but still it is required due to the high power levels of the laser beam. LIDT of this coating is 1.5 gigawatts per squared centimeters for 1064 nanometer, pulse width 20 nanoseconds. Now we'll go to the next topic, which is annular beams. So annular beam means that the distribution of energy has a ring-like shape, like in this diagram. You see that the energy is distributed in a ring-like pattern. In the center, there is no laser beam, no laser energy. All the laser energy is concentrated in this ring. Now we can control the diameter of the inner ring and the width of the ring and the outer diameter of the ring. And if we use annular beams, what we achieve is that we can cut thicker materials, because the energy is not distributed all over the area, but only on a small part of the area. So we can optimize the beam distribution to achieve very good cut even at thick materials. This is the basic idea of why to use annular beam. You distribute the profile of the beam in such a way that the cutting process is optimized. Now, we can design and manufacture the optics required for annular beam, but in order to do that, we must know all these parameters. So these parameters should be specified by the customer in order for us to design and manufacture the right optics to generate annular beam. So the parameters include the following. First of all, laser wavelengths, then laser power range, laser BPP. BPP is beam parameter product, which means the quality of the beam. Then laser fiber core diameter, collimator lens focal length, focusing lens focal length, what is the annular beam outer diameter required, and what is the annular beam width. So if you specify all these parameters, we can design and manufacture the right optics to give you the right annular beam. And by doing this, you will achieve the optimal cutting conditions. Okay, the last topic is zoom optics. What is zoom optics? Zoom optics means that we have a lens that its focal length is not fixed but continuous from minimum value to a maximum value. By using this zoom lens, we can achieve a variable spot size which fits the full range of required sheet thicknesses in a single lens. So one lens is good for all cutting conditions. And we can get efficient cutting at each thicknesses with the same lens. This gives us the ability to change the focal length by pressing a button without opening the sealed housing of the cutting head. So consequently, there is no exposure to contamination, the machine is still running because we only have to push a button. We do not have to replace the lens, and therefore no lens alignment is required when you change the focal length. Single lens for all cutting conditions, as I said, continuous focal length change, and also we can have smaller movement required to shift the focal plane. So with this lens, the zoom lens, we can also control the position of the focal plane, and we will see an example soon. So this is a layout of a zoom lens, and we will now see how it is operating. I will show you a set of slides in which slide the position of the lenses will be changed, and consequently the function or the result beam, the beam which will leave the lens, will be changed. So first we will see how to change the focal length of this zoom lens, and this will be achieved by moving these three optical elements. Now you can see the diameter of this beam, and you will see that the diameter of the beam will be changed as a function of the position of these lenses, which means that the focal length of the lens is changing per the position of these lenses. Now see the slides. You see that the lenses moves from here to the left, and the diameter here is decreasing. Let's see the next step. Another movement, and diameter is getting smaller, smaller and smaller. This is another movement, another change in the focal length. Another movement, still focal length changing. Another movement, the diameter is still decreasing. Another movement, still decreasing. Another movement, another movement, another movement, and this is the final movement. See that diameter here is minimal, and now let's move them again. You see these three elements going now to the right, and this diameter is increasing. Watch. So this is how the zoom lens is operating. The principle is that by moving the position of lens element, you control the focal length of the lens continuously, and consequently you control the spot size on the metal you are cutting, and in this way you can achieve the optimal cutting condition for each material and for each thickness, again with a single lens. Let's see it again. Okay, now the second function of a zoom lens is changing the focal plane. Here the focal plane is in this location. You notice that when we change the focal length, the focal plane position did not change. However, now we will change the position of this lens, and this lens controls the position of the focal plane. It doesn't change the focal length, but it changes the focal plane position. Let's see it. Watch this lens movement and the position of the focal plane. Watch. Okay, I will show it again, but the principle is that as you move this lens, the BFL, the back focal length, is getting bigger and bigger. So the position of the focal plane is changing continuously. Let's see it again by moving to the other side. Okay. So, in summary, if you move this set of 3 lenses, you change the focal length of the lens without changing the focal plane position. However, if you move this element, you change the focal plane position, but you are not changing the focal length of the lens. This is the principle of a zoom lens. And actually, we designed such a lens. You can see the lens we designed and manufactured here in this picture. Here you can see the water cooling channel. The water cooling is required if you want to operate the lens for high power lasers of 6 kilowatts and above 6 kilowatts. You must cool down the system by water. You have here motors. You have a lens controller, a PCB, which controls the movement of the lens elements. And you can achieve, as we saw, a change in both in the focal length and focal plane position. This slide shows cutting test results using our zoom lens. On the left side, you see some shapes we cut with this lens. On the right side, you see the zoom lens operation. You see here that the cutting width is changing according to the focal length of the lens or the magnification of the lens. Here, you see that the width is maximum, and this corresponds to a magnification, lens magnification of 2.4x. If you change the magnification or the focal length to 2.2, you get this cutting. If you change the magnification to 2.0, you achieve this cut. 1.8 magnification, this width. 1.6, you achieve this. 1.4 magnification, you get this width. 1.2 magnification, this width. And 1x magnification, you get the most narrow width of the cut. So according to your application, you can choose which width you would like to have, and accordingly you adjust the lens so you get your optimal cutting conditions. This is the principle of a zoom lens. As you can see, it's very convenient and it's very useful. In order for us to design the right zoom lens for you, we needed to know these parameters, and we will go through them, through the list. First parameter we have to know is fiber laser core diameter, then fiber laser BPP, then collimator lens focal length range. What is the focal length range you would like to have? What is the focusing lens focal length? And actually the combination of these two focal lengths result in the spot size range you will achieve with the zoom lens. So if you specify, for instance, that you want to achieve spot size range of between 100 micron to 400 micron, you specify it here, and then we can design the focal length accordingly, so you will get the required spot size range. In addition, you should specify also what is the focal plane shift range you would like to have, plus minus 10 millimeters, for instance, or other values, so we can know what is the required movement of the lenses. We also must know size and ICD requirements you might have, mechanical interface, electrical interface, and communication protocol to use and activate the lens. So if you specify all these parameters, we can design and bid for you the right zoom lens according to your specifications. Any questions? Okay. I don't see any questions here, but again, I will show you the first slide so you can see again my email address. Here is my email address. Please send me emails with questions or comments you have. Thank you very much, and bye-bye.